Okay, so today I want to talk about trigonometric integration. And this is a lovely technique for computing some integrations where you have something that looks, like it's some related to a right triangle. And you can see inside here are the square root, which we'll talk about how it's related to the Pythagorean theorem. And I want to really walk through trigonometric integration by using logic, not necessarily memorization. And I want to do that for two reasons. One, it's extremely helpful. You remember it longer. If you're stuck on an exam problem, if you really understand what's going on, you can manipulate it much better. The question to make it simple, more simple. So let's start. I see right away that using u sub wouldn't work. You'd get an x squared on the bottom, and you get a u on top. So you can integrate with respect to du. So if you want to look at that, I suggest you try to try to use u sub on it and see what happens. Right away, I see that we have something right here, and I see that if I look at the Pythagorean theorem, which is equal to c squared, if I solve for one of the other sides, so let's just say we solve for b, I'm gonna call I'll do that in a bit. We're gonna b is equal to the square root of c squared minus a squared. We see that c is clearly x, so the hypotenuse is x. And we have some minus some side, and I'm actually going to get rid of that. I'm going to call it, because we don't know what side. We don't know exactly which side this is. Is it A, is it O, is it adjacent, is it opposite? We don't know. So I'm going to call it side, and we're going to call this just, let me think of some random variable. Okay. So we have, squared, some side, we don't know what it is. And we see that we can relate this back to this. We get some side is equal to the square root of x squared minus k squared, right? And we see that k squared is just 5 squared. Because if you square 5, you get 25. So let's replace this with 5 squared. Okay. So we have this, right? So we see that we can clearly relate it to a right triangle. And that's really where this top part of the integral came from. So we see that if we can relate this back maybe with some angle phi, it might simplify this integral. So let's try to do that. So let's draw a right triangle. Call this angle phi, and basically we know that this is x because this is the hypotenuse, right? We solved for it and we shown that this was x, and we know one of these sides is 5. We don't know which side. We know one is not 5. So let us think about it. Let's see if we try sine, right? If we try to relate this by sine, x by sine, let's see if we use sine, the angle is equal to the opposite divided by x, which is the hypotenuse in this case. And we see if we solve for x, right? If we solve for x, we'll get a sine of phi in the bottom. And that's a pain to differentiate, right? And to manipulate and to use. Let's try, next thing I'm going to try is secant. Because I saw that if we get x on top, we can just times it by whatever's in the bottom of the right-hand side. And you'll see what I'm talking about in just a moment. So we're going to get that secant of phi is equal to x divided by adjacent. We see that right away we can solve for x. And we know that a is 5, right? Because it's just, we want to use it the variable that we know. So we're going to get 5 secant of phi. Okay, so now that we have this, we know that this is adjacent. So our 5 is our adjacent. And we know that this is our side. And I'm going to do this in green. So let us now relate this integral to this new value we found for x by using trig sub. Right? We subbed in trigonometric relationship. We use a trigonometric relationship to relate this to phi. Right? X is exactly this by this triangle. So we're going to get kind of messy. Well, x is now what? X is now this, right? So we're going to substitute that in. 5 secant of phi. And we're going to get this value squared, right? We're subbing x if we square both sides. So if we square this, we're going to get 25. Secant squared of phi minus 25. So we can now factor out a 25 from both sides. But before that, we want to integrate with respect to d phi now, right? Our variables are phi now. Everything else is constant. And we have a dx still, right? How does dx relate to d phi? And that's really the important thing. We want to relate this differential amount to d phi. What is this exactly equal to relative to this? Well, we can take the differential of this. Let us do that. So I'm going to put in here parentheses because we want to relate dx to d phi. How are these related? So I'm actually going to need some room. I'm going to copy this. And because I want to be very clear about this. Very important concept. Okay, so take the differential. X is equal to 5. What's the differential of secant? It is actually secant of phi, tan of phi, and then the differential is d phi, right? Okay, so now we know that, so we can just substitute that in there. And that's how dx, right, relates to d phi. Bam. So now we can simplify this. So we see that we have 5 secant of phi and 5 secant of phi. So this crosses out, and we're left with tan, and up here we have this. So let's try to simplify this. Let us now write down the integral again. And we have nothing in the denominator anymore. So we're going to have the square root of 25 secant squared of phi minus 1. And now we're going to, now we just have a tan of phi d phi on the outside. We see that we know the square root of 25 is just 5. We can pull that outside of the integral. We're going to have phi integral of secant squared minus 1 now. And then tan phi d phi. So this is our integral now. And well, what can we do with this inside? I know some some beautiful trig relationship, and I'm sure you all know it too. It's cosine squared of phi plus sine squared of phi equals 1. Now, if I divide everything by cosine squared, well, cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared is tan squared. And 1 divided by cosine squared is secant squared. I can now minus 1 from both sides, and we're going to get tan squared is equal to secant squared minus 1. So we can substitute that back in, and then we're going to take the square root of tan squared, which is just tan. So we're going to have tan here. So we see that this is equal to tan of phi, because it's going to be tan squared, square root is just tan. So tan times tan is tan squared. So now we're going to get our integral is tan squared of phi d phi. Okay, now I don't in fact know this integral, but I do know the integral. I do know that the derivative of tan squared is secant. Let's move this. I do know that d over dx of tan of phi, is equal to secant squared of phi. And I can see up here that if I relate tan squared back to this, if I integrate this, right, integrate both sides, I'll get this. So I'm going to make this up. I'm going to say this is the same thing as the integral of secant squared of phi minus 1 d phi. And I know that if I split this up into two integrals, which is what I'm going to do, secant squared phi and this is, well, we know if we differentiate tan of phi, we get secant squared of phi. So if we go backwards, we're just going to get tan. So now we know that this is going to be 5 times secant squared of phi, which is now tan of phi, minus phi, and then plus c. Now you should think about why does it matter if you put c in here, c over there. It's just some constant, right? If you put it inside, you're going to say it's 5 times c, but c in that case could just be 1/5 its original value. So it's the same thing. It's the same thing whether you times it by 5, divided by 5, doesn't really matter. It's still a constant. Okay, so now we have this. But we want this integral with respect to x, right? So let's relate this back to the triangle we found above. And if you remember the triangle, if you wrote it down maybe, you know that the triangle has an angle phi. We have the x, which is the hypotenuse, and we found 5 to be the side, chose this to be the adjacent, and we know that this is some side. So tan of phi is equal to opposite, which is the side, divided by 5. What's the value of this side, right? Well, if we use a Pythagorean theorem again, we have a squared plus b squared equals c squared. And this is in case, sorry, can't even speak. In this case, it's going to be 5 squared plus b squared, and I'll call this s squared, is equal to x squared. We can now get s is equal to the square root of x squared minus 25. So this is equal to 5 divided by the square root of x squared minus 25. Sorry for that poor penmanship up there. Okay, so we're now going to bring this down, and we're going to get 5 is equal to, see that tan is equal to that, and we see that we're going to simplify this out, obviously. I love simplifying things. Minus 5. Well, this is interesting. We could take an arctangent and solve for it, right? Or one of the arcs, right? We could use one of the inverse trigonometric functions, and that's exactly what I'm going to do. Let me move this over. I'm going to move this all over. I'm going to shrink it down. Let's do, I like sine. I'm a big sine guy. So sine phi is equal to opposite, which is s. I think using cosine would be easier because we have this and this. It wouldn't be such a pain to write. So let's use cosine. So we have cosine. Stress in here. Phi is equal to 5 divided by x, right? Because this is the hypotenuse, this is the adjacent. We're going to take the arc of both sides. We get phi equals cosine of 5x. Okay, so we now know that's going to be arc cosine of 5x. Remember, these are the same. Plus c. Now let's factor this through. Right, this 5. So we're going to get the square root of x squared minus 25 minus 5 arc cosine of 5x plus some constant. And that is our integral. We just solved for the integral, and if you don't remember the integral we solved for, this is the integral of the square root of x squared minus 25x dx. Anyways, thank you guys so much for watching. Hope you guys have a great day. Please like and subscribe.